Hi, this is Christina, inviting you to come and join me.
Welcome to the Deep Dive, folks, where we sift through a stack of solid sources to bring you the most eye-opening insights, all tailored just for you. Today, we're pulling back the curtain on a downright pivotal, often behind-the-scenes technique that's helping put powerful AI right into more hands. You've probably heard the chatter about the large language models GPT-5, Gemini, maybe DeepSeek. Their know-how is out of this world. They write, they code, they sum up details, and crank out creative content. But behind that swell performance, there's a real challenge lurking.
Oh, no question about it. These models are marvels of engineering, sure, but their colossal scale means they guzzle computing resources like nobody's business. We're talking mountains of storage, hefty memory needs, and processing power you'd expect from a high-end server room. That turns into steep operational costs. It's hard to roll them out widely or run them on your home machine. And that's a big obstacle for broader innovation and individual creativity. But what if we could corral much of that same smarts without paying for all that massive, pricey infrastructure?
Exactly the mission for today's deep dive. We're putting the spotlight on quantization. It's proving to be a genuine game changer, letting some models run smoothly on devices you already own, your desktop, laptop, even your phone. We'll lay out what it is, how it works, and the real trade-offs and benefits. Let's start with the big question. Why are these models so large in the first place? They're incredible, sure, but you call them digital behemoths. Could you break down the actual costs and demands that keep them out of reach for everyday personal use?
Absolutely. Imagine trying to run a supercomputer right in your den. That's what it feels like. These models pack billions, sometimes hundreds of billions of parameters. Think of them like all the tiny knobs and dials that store the model's know-how. Each parameter is a number, and traditionally they're stored with high digital precision. That makes for enormous files, often hundreds of gigabytes, that must be loaded into your VRAM just to get started.
Hundreds of gigs just in memory, goodness.
Exactly. And beyond storage, you need muscle under the hood. Often, specialized GPUs are almost a must, capable of handling trillions of calculations a second. And it's not just the upfront cost. You've got energy consumption, heat output, and the time it takes for every single interaction. For most people or small outfits, it's just not workable.
Right. And that's where quantization, our star player today, makes its entrance.
You bet. It's an elegant answer, or at least a big part of one.
All right, straight shooter question. What exactly is quantization when we're talking about LLMs?
Simply put, quantization means mapping a large or continuous set of input values to a smaller, more discrete set. In neural networks and LLMs, it almost always boils down to reducing the precision of the model's weights and activations, those numbers that shape its learned patterns and determine how it answers your prompts.
So we're taking these highly precise figures.
That's right.
And making them less detailed in terms of digital storage. Give me a concrete picture. What does that reduction look like?
The most common move is to start with 32-bit floating point numbers, FP32 for short, and bring them down. FP32 gives an enormous range and precision, but we can quantize down to 16-bit floats or even 8-bit integers, INT8.
Okay.
Think of it like shrinking a massive paint palette. Instead of thousands of subtle shades, maybe you stay with 256 colors or even just 16. Every reduction step, say from 32-bit to 16-bit to 8-bit, slices your storage needs and speeds computation because the processor has less data to shuffle.
Sounds first rate. Less storage, faster speeds.
Exactly.
But there's always a trade-off. You're tossing some information overboard. What's the rub?
Exactly. The rub is you might see a small drop in the model's accuracy or performance.
Oh.
Compress those numbers, and you lose some fine detail the model learned. The trick, and the hot topic among researchers, is finding the sweet spot.
The sweet spot. You are great at finding that.
Yes, the balance where you get maximum size reduction and speed without harming the model's usefulness or output quality too much.
So by hitting that sweet spot, these massive models could run right on my desktop, laptop, maybe even my phone, and still keep almost all the performance? Sounds nearly too good to be true. Are there situations where that sweet spot is tougher to hit?
It's a remarkable leap forward for accessibility. Finding the absolute bullseye sweet spot is still under study, but many models have surprising redundant precision.
Redundant precision.
Yes. Picture painting a masterpiece with millions of brushstrokes. When you stand back, plenty of those individual strokes just blend away.
I follow.
In the same way, much of an LLM's ultra-fine numerical detail doesn't add proportionately to how good its answers seem to a human reader. Sure, there are situations, like sensitive scientific work or exact number engineering, where every scrap of precision matters. In those cases, quantization might not be acceptable, but for most general-purpose language work, the gains usually outweigh the minor losses.
That painting image drives it home. Now help our listeners pin this down with a basic example. Let's use that case from the sources. Quantizing a matrix from FP32 down to INT8. How's it done?
Certainly. Picture a large grid, a matrix of numbers, representing a small slice of the model's brain. Each number is FP32 32-bit floating point. That gives you an astonishing range of values, stretching from tiny fractions to astronomical amounts, like 3.4 times 10 to the 38th, both positive and negative. It's a scale so fine-grained it boggles the mind.
Wow, that is a lot of possibilities for just one number.
Yep.
Well, that's a level of detail almost beyond comprehension. How does that stack up against the 8-bit integer set?
The 8-bit integer set, or INT8, is a whole different ballgame. It's far smaller, just 256 distinct possible values. Usually, that's the whole numbers from negative 128 up to positive 127.
Great.
So you're taking that enormous, smooth spectrum of billions of possibilities and squeezing it into just 256 specific points.
An ocean into a teacup, you might say. How do you pull that off without losing so much information that the model comes apart at the seams? What's the move?
Exactly. The secret is smart scaling and mapping, not guesswork. First, you scan your original 32-bit matrix to find the single biggest value, ignoring whether it's positive or negative. Let's call that X-max.
All right, X-max, the heavyweight number in the bunch.
Exactly. That X-max sets the bounds for the meaningful data in that matrix.
Got it.
Then you scale. You take that whole span from X-max to X-max and shrink it so it fits neatly into the INT8 range of negative 128 to 127. After that, each number gets rounded to the nearest available integer in that 8-bit space. The aim is to keep the relative relationships between numbers intact, even though we've trimmed away some absolute precision.
So the relationships survive the trip.
Right. Like redrawing a world map at smaller scale. It's less detailed, but all the cities and coastlines are still right where they belong in relation to each other.
I like that map picture. Makes it clear we're talking careful compression, not haphazard chopping. Now, theory is fine, but let's roll into what happens in practice. Our sources have sharp data showing the trade-offs and payoffs. First stop, compression versus perplexity. Perplexity, for those not steeped in the term. It's essentially how surprised the language model is by a stretch of text. Lower perplexity means the model's more confident, more fluent. Lower is better.
Exactly. And there's a telling chart from a study. The horizontal axis is quantization applied, and the vertical axis is perplexity. You can see that perplexity generally creeps up as bits drop. In this study, the gap becomes more noticeable around INT3 and below, while INT8 and INT4 are often close to the original model, just a touch more puzzled.
So trimming size often means a small ding in fluency. Makes sense.
Yeah.
But here's the kicker. Our sources show that the first level of quantization often cuts a model's size while barely nudging perplexity. It works almost just as well.
Exactly.
That's a staggering efficiency gain right out of the gate.
It is, and that's where redundant precision comes into play, just like we discussed earlier. That full 32-bit, even 16-bit precision in much of a model contains details that just aren't mission critical for its language skills, at least not enough for a human to spot the difference. Imagine a high-resolution photograph. If you shave a bit off the color depth, most folks' eyes won't notice, but the file size drops a lot.
Okay, nice analogy.
That first quantization step is truly low-hanging fruit in optimization, a big win with almost no downside.
All right, beyond size, speed matters hugely for hands-on work. Let's check inference speed for, say, a 7 billion parameter model. How's that measured and what do we find?
For inference speed, the measure is time to first token TTFT. It's basically how fast the model starts producing words after your prompt. Another measure is tokens per second, how quickly the rest of the tokens stream out.
Got it.
The baseline 16-bit floating point, already trimmed a bit from 32-bit, posts 116 milliseconds for the first token.
116 milliseconds, okay.
Apply 2-bit quantization, quite aggressive, and you slash that to 56 milliseconds for the first token.
56. That's less than half the time.
Exactly. A dramatic speed up. The heavier the quantization, the faster the model can churn through data and spit out answers.
Half the time to produce each token. That's a turbo boost, especially for interactive use. But here's the question that matters most for most folks. What about quality? Can someone really tell if they're chatting with a full precision model versus a heavily quantized one?
That, without a doubt, is the critical question. And our sources bring some truly eye-opening insights to the table here. One site, linked in the original video we reviewed, ran a very thorough and costly comparison. They had experts put models through their paces, models quantized all the way from 2 bits up to 8 bits, tested across a broad array of topics, science explanations, coding challenges, ethical scenarios, plain old common sense reasoning, a real mixed bag.
All right, so a genuine workout for these models. And after all that scrutiny, what was the verdict? Did the experts spot clear flaws in the quantized versions?
Here's the remarkable part, something that really upends the usual expectations. The experts said, and I quote, "They were experimental findings indicate that while 4-bit quantization maintains performance close to non-quantized counterparts, a notable performance discrepancy emerges as quantization decreases to 3 bits or lower."
Wow.
And even more surprising, for many, maybe most common use cases, 4-bit quantization is quite likely more than enough.
That's truly extraordinary.
It is.
So, for all practical purposes, we can grab those major efficiency gains, smaller size, faster speed, without giving up what counts most for the end user, the quality and usefulness of the AI's output. It does make you wonder why we needed all that ultra-high precision in the first place if people can't really spot the difference in many cases.
Indeed, it opens a fascinating line into both cognitive science and AI alignment. One idea is that human language processing works at a level of abstraction where extreme numerical precision simply isn't necessary to convey meaning or coherence. Our brains are adept at filling gaps and reading context. So long as the main learned structures and core knowledge survive quantization, those subtle numerical differences may slip completely under our perceptual radar. It also shows just how robust these large models are. They seem to carry built-in redundancies that let them run strong, even under heavy data compression.
All right then, let's thread this together. For you, the listener, the builder, the curious mind, what's the real takeaway here? What's the big picture?
When you zoom out, quantization is democratizing access to powerful AI. That's the heart of it. It's turning resource-hungry behemoths into leaner, faster, and most importantly, personal tools.
Exactly. And for you, that means those aha moments, those rich interactions with AI, aren't confined to giant data centers anymore. Soon you could be running highly capable LLMs like the ones we've talked about right on your laptop, perhaps even your tablet. That means faster, more private exchanges with cutting-edge AI, since your data might never need to leave your own device.
Right.
It also means more cost-effective builds for developers, and a world where advanced AI doesn't just belong to the tech titans, it's in reach for everyone. Near full performance at a fraction of the size and cost. That's a whole new era for personal, accessible AI. And to think, it all comes from a deceptively simple lever, lowering numerical precision.
It's a fine example of ingenuity in action, constantly optimizing, innovating, and challenging the old assumptions. Work like this keeps advanced AI from being fenced in by traditional resource limits and pushes the boundaries of what we can run on everyday hardware.
Absolutely. So as we wrap our deep dive, here's a thought to take with you. If today's AI can keep virtually the same performance even at sharply reduced sizes, what other hidden efficiencies might be waiting in the wings, in digital systems, in biology, just sitting there, ready for discovery? And what would those breakthroughs mean for the next wave of technology that touches every corner of our lives? We've enjoyed this journey into the world of LLM quantization. Stay curious, keep learning, and we'll see you on the next deep dive.
Hope you enjoyed listening to, well, my voice. If this was useful, hit subscribe and share it with a friend. And there's a little extra for you in the show notes or description.